Hey there, Year 12s. Welcome to this explainer. Think about what you've already done today. Maybe you sent a message to a friend, checked a website, or streamed some music on your way to school. But have you ever actually stopped to think about the sheer complexity behind sending a single email or booking a flight? We interact with these massive, invisible, and honestly incredibly complex networks every single day without a second thought. But as future IT professionals, it's time to stop just using these systems and start understanding exactly how they operate under the hood.
Today, we're diving headfirst into Unit 12.1, Information and Communication Systems. We're getting right to the good stuff, the core concepts from your textbook that you absolutely need to know for your exam prep. My goal today is to make these concepts crystal clear so you can walk into those assessments with total confidence.
Here's our game plan for today. We'll be hitting 5 main areas. First, defining communication systems. Second, essential hardware and protocols. Third, methods of connection. Fourth, accessing the internet. And finally, real-world applications. Let's get right into it.
All right, Section 1, Defining Communication Systems, Making the Invisible Visible.
So what exactly is a communication system? Basically, it's the various processes that enable information to be passed between people. Now pay close attention to that word processes. A system isn't just the laptop sitting on your desk, it is the entire end-to-end journey of moving information from point A to point B. And these systems can be super simple or incredibly complex with a whole bunch of different hardware devices working together behind the scenes to make that communication happen.
To wrap your head around this, think about a traditional, old-school mail network. To send a letter, you need 4 key things. First, a person to actually start the communication. Second, a method of contacting them, like a physical home address. Third, a method of forwarding, which is the written letter itself. And fourth, a method of delivery and receipt, like a postal worker dropping it into your physical mailbox. Well, digital networks use that exact same logic. You're the sender, the IP address is the home address, the data packet is the letter, and the servers and routers, they're basically your digital postal workers.
Moving on to Section 2, Essential Hardware and Protocols, or, as I like to call it, the vocabulary of networking.
Okay, first up is a word you've definitely heard, the modem. But did you know it's actually a mashup of 2 different words, modulator and demodulator? See, computers speak in digital signals, just ones and zeros. But older telephone lines were built to carry analog signals, like the sound waves of human voices. So a modem's job is to act as a translator. It converts your computer's digital bits into sound frequencies that can physically travel over a copper phone line, and then the receiving modem translates those sounds right back into digital bits. Crazy to think about, but early dial-up modems operated at just 300 baud. That meant they transmitted only about 300 characters per second using distinct audio frequencies for a 1 and a 0. Wild, right?
So once your data is actually on the move, how on earth does it know where to go and how to behave? Enter TCP/IP. That stands for Transmission Control Protocol and Internet Protocol. Basically, this is the fundamental set of rules, the universal language for the entire internet. And what's really cool about TCP/IP is that it was developed by the industry generally. No single company owns it. It provides the addressing scheme that allows billions of devices to have completely unique addresses, which is what lets clients and servers communicate so seamlessly all over the globe.
Now let's look at how that data actually flows. We've got 2 main types of transmission here, synchronous and asynchronous. Synchronous transmission is exactly what it sounds like. It sends data between devices in a steady, continuous stream. Asynchronous transmission, on the other hand, sends data in spurts. It fires off a bit of data and then actually waits for a response from the receiver before continuing. ISPs and consumer modems rely heavily on these specific transmission types to manage traffic and make sure your connection doesn't just completely buckle under pressure.
But what happens if a wire gets bumped or there's some random interference, and a 1 accidentally flips to a 0 while it's traveling? That is exactly where the parity bit or check bit comes into play. You guys, this is such a brilliant yet beautifully simple way systems make sure data isn't corrupted. By slapping just 1 extra bit onto the very end of a string of binary code, the receiving device can do a really quick mathematical check to see if the data arrived exactly as it was sent. It is a foundational form of error detection.
All right, Section 3, Methods of Connection, the physical and wireless pathways.
So there are some pretty stark physical differences in the cabling we use. On one side, you have the standard UTP, or unshielded twisted pair cable. This relies on good old-fashioned copper wires twisted together. But then, on the other side, you've got the totally futuristic look of a fiber optic cable. This thing is literally made of microscopic glass threads that transmit data using actual pulses of light.
Let's put them head to head. UTP, like your standard Cat5 or Cat6 Ethernet cables, offers really solid bandwidth, up to 1 gigabit per second for Cat6. Plus, it's cheap to produce and incredibly durable, which makes it absolutely perfect for local home or school networks. The downside? Its signal degrades over distance, usually maxing out around 100 meters. Now, fiber optic, because it uses light instead of electricity, has a vastly higher bandwidth. It can carry data for up to 100 kilometers without losing any signal. But the trade-off is that it's way more expensive to install, and those tiny glass threads make it significantly more fragile than copper.
But hey, we don't always use physical cables, right? For vast distances or super remote areas, we rely on wireless pathways, like satellites. These systems use microwave technology. And because microwaves have very short wavelengths, they require a direct line of sight to function. They can't just magically pass through mountains or heavy trees. For internet access, we use geostationary satellites. These orbit the Earth at the exact same rotational speed as the Earth itself, so roughly 24 hours. This means that from the perspective of a dish down on the ground, the satellite appears completely stationary up in the sky.
Section 4. Accessing the Internet. Bridging the gap.
You know, to really understand how we connect today, it helps to look back at how we used to connect using legacy dial-up. It was a very literal, step-by-step process. First, software on your computer would physically dial a phone number. Second, your modem would convert your digital data into an analog sound signal. Third, that sound traveled over fixed phone lines to a whole bank of modems at your internet service provider, or ISP. And finally, the ISP would convert the signal back and provide your bridge to the broader internet. It gave you a dedicated line, sure, but man, was it slow.
Now contrast that clunky old dial-up method with the modern broadband cable connections we use today. Cable uses coaxial lines, which is often the exact same infrastructure used for pay television. The big advantage here? Vastly higher speeds and much better reliability compared to dial-up. But there is a catch. Cable broadband is often a shared service in your neighborhood. So if everyone on your street gets home at 5 p.m. and starts streaming video all at once, that massive spike in demand can actually slow down the service for everybody.
And finally, Section 5, Real-World Applications, Systems in Action.
Okay, let's look at a standard printer using Bluetooth. This is a perfect illustration of a consumer-level communication system. Bluetooth is a low-powered wireless tech designed for very short distances. It allows devices like our mobile phones, headsets, and printers to instantly form miniature, temporary networks. It's just a fantastic example of a highly localized communication system that makes our everyday tasks completely seamless.
But then, on the complete opposite end of the spectrum, you've got massive enterprise networks, like an airline reservation system. Your textbook brings up examples like Air Niugini. Just think about the sheer volume of data passing through this kind of system. It has to simultaneously handle real-time inventory for thousands of flights globally, pair availability with cities, securely process passenger name records, calculate complex fare data including taxes, and instantly issue electronic tickets. Pulling that off requires incredibly robust servers, high-speed fiber optic connections, and rock-solid TCP/IP protocols to make sure that when you click book, someone halfway across the world doesn't get double booked in your exact seat.
I want to leave you guys with one final provocative thought. As your textbook points out, there is currently no such thing as a perfect communication system. Every single system has performance issues. Physical mail gets lost, telephone networks get damaged, and email systems suffer from latency, server outages, and of course, endless spam. So will there ever be a truly perfect system? Well, as you study these concepts, remember that these vulnerabilities and limits are the exact problems that future IT professionals, like you, are going to be tasked with solving. Good luck with your exam prep, Year 12s, and keep questioning how the invisible world around you really works.